Yeah, so thank you very much. I'm very happy to be here on this very special occasion. So I will discuss some joint work with Sandro Vera. On K-free surfaces of genus 14. And to put things into context, I will recall a very well-known work of Mukai. So Mukai, in a long series of papers, so I would say from 1987 to 2013, he established structure theorems for polarized K-free surfaces of small genus. So structure theorems for general polarized K-free surface of genus G. So this is a K-free surface. And so the genus is the, so H squared is 2G minus 2. And this is something I call a K-free surface of genus G because the hyperplane sections are canonical curves of genus G. And in particular, he established structure theorems for the moduli space of such polarized K-free surfaces. So this is the moduli space of polarized K-free surface of genus G. And unfortunately, unlike for MG, here there is no uniform notation for this moduli space. Some people denoted MG, which I find not such a brilliant notation. So I will use this Mukai notation, FG. Okay, so now this is Mukai really. So let me recall the best known part of Mukai's work, and this is the one that he did early on for these genera. So this is a case-by-case story. There is no uniform construction. But in these cases, Mukai discovered the existence of a variety, which again I should call MG, Mukai variety. But so VG, a Mukai variety, this is a rational homogeneous variety in projective space. So this is of dimension NG, and it is in PG NG plus G minus 2, which has the property that the canonical of this is O of 2 minus NG. And now the main point is that if you look at linear sections of this VG of dimension 2, so two-dimensional linear sections, of VG, well then of course it's easy to see that you get K-free surfaces. The canonical bundle is 0 by the adjunction formula, but Mukai showed that you get all K-free surfaces. So you get all genus G polarized K-frees. Oh, I mean you get almost all. You get a generic one. And right. In fact, how much you don't quite get all will play an important role in this talk. Right. So rational homogeneous. So in particular, this gives a realization, a very simple and concrete realization of the moduli space. So FG is isomorphic then to, birationally isomorphic to a Grassmannian. So you look at the Grassmannian, so you are in this projective space. You cut it with a G-dimensional projective space, so this is the projective Grassmannian. So you look at GG NG plus G minus 2. And then, of course, you have to mod out by the automorphism of this Mukai variety. And you have a birational isomorphism. So this is a tremendously useful theorem. In some sense, if you are interested in K-free surfaces of a small degree, you cannot escape this theorem, right? Because it really, it's kind of the canonical incarnation realization of the K-free surface of genus G. So let's do an example which will be important for some reason later on. This is G equals 8. In this case, V8 is the Grassmannian of lines in P5. This is part of the Mukai package. This is embedded in P14 via Plücke. So the dimension N8 is 8. And you are in P14, as it should be. And this procedure here gives a realization of the moduli space F8 of polarized K-free surface of genus 8 as a Grassmannian G8 14 modulo the automorphism of the Grassmannian, but the automorphism of the Grassmannian is, of course, PGL6. Yeah, so if you want to check dimensions, so this is, you know, affine G9 15, so this is 54 minus 35, 19 dimensional. So both are 19 dimensional. So they have a chance of being isomorphic, and they are birationally. Right? So this has basically, you look at the Plücke embedding, you take you intersect the Grassmannian with a P7, and you get a K-free surface. You get a generic K-free surface in this way. And of course, you can go one dimension lower, and then you will get canonical curves, and it's part of the Mukai package, and I will use this. That's M8 is, in fact, again, birationally isomorphic. So this is the moduli space of curves of genus 8 with the Grassmannian G7 14 modulo PGL6. And with a bit of effort, I can now go some way towards answering Kieran's, addressing Kieran's remark. You can put some bars here with a little care. It's not totally understood how this Mukai construction behaves on the boundary of M8, but on some stable curves, it is understood that it will be important in what I'm going to do. So this is Mukai around 87. Then, of course, time goes on, and there are other cases, and these cases are genus 12, 13, 18, and 20. So everything is almost the same. So Mukai has analogous, I mean, for each genus, Mukai has a paper, right? And actually, for this is true. Maybe 18 and 20 did in one paper. And there is a Mukai variety in each case. And then there is a VG, and there is epsilon or EG homogeneous vector bundle on VG such that the K-free surfaces are K-frees of genus G are essentially linear sections of sections of this vector bundle. So it's a little bit more complicated. There is another vector bundle in the picture, but essentially the same story. And then there is even more close to our days. So these are Mukai's last papers on the subject, genus 15 and 16. Ah, yeah, so I should have said something. So this is some sort of Grassmannian always. Sometimes it's an honest Grassmannian, sometimes it's an orthogonal Grassmannian, and so on, but it's a Grassmann variety. And then genus 15 and 16 station is more complicated. The same works, but in this case, VG is some Hilbert scheme of curves. Hilbert scheme of some curves. This is a complicated story. So, I mean, Mukai, when he gives a talk, I mean, he just dedicates 1 hour for one genus. So, in any case, the structure theorem is there. And as a corollary, you have that Fg, the moduli space, is at least unirational, but you know much more, of course, that it is unirational for all these values. Okay, so this is the situation. So you see what is missing from this classification. Actually, these are the only values, I should have said this, of Fg which are known to be unirational. We don't have other constructions other than Mukai ones. What is missing from this classification is, of course, G equals 14. Yeah? And for G equals 14, there is no known structure theorem for K-free surface of that genus. So, and this is the subject of this talk. So the theorem with, so Janos said that I should, if I want to write something that he doesn't see, I write here. So, well, I have right here on top. So this is the main theorem of the paper. This is with Vera. That if you consider, you can always consider the universal K-free surface. So this is Fg1 over Fg. So this is the universal K-free of genus G. So here points are triples SHP. So SH is a polarized K-free surface and P is a point on S. So this is a 21-dimensional moduli space. The universal K-free surface of genus 14 is rational. So we have some way of understanding K-free surfaces of genus 14. And I will explain the proof of this theorem. But so this talk will not provide a structure theorem for K-free surfaces of genus 14. I mean, we did not really expect to be able to beat Mukai at his own game. Instead, it understands K-free surfaces of this genus via cubic fourfolds. And now I have to make a little detour into the world of cubic fourfolds and understand and explain how this is possible. So this was so far a summary why genus 14 is relevant in this situation, because it's the first genus where we don't know the situation. So cubic fourfolds. Oh, 11. 11 is known. 11, we know tons of things about it. So for 11 does not fit in this picture. There you have that M11, the moduli space of curves of genus 11, is a P11 bundle over F11. And this picture with the non-abelian Brill-Noether theory. In some sense, that is the most beautiful of all cases. It doesn't fit into this picture, but you do know. So M11 is definitely unirational, so F11 is also unirational, and you have this F11 as the basis of this non-abelian Brill-Noether fibration with source M11. So there are really no other exceptions. Cubic fourfolds, right. So there is a 20-dimensional moduli space of cubic fourfolds. Cubic fourfolds, X3 in P5. And this is, of course, just the quotient of the linear space. Maybe you take the smooth ones if you want, and you mod out by PGL 6. So this is 20-dimensional thing, variety. And Voisin proved for such cubic fourfolds the integral Hodge conjecture. So you know that if you look, so for X3 in P5, a cubic fourfold, if you look at the group of middle Hodge classes, this is just the Chow group of codimension 2 cycles. And you also know that if you have a general, cubic fourfold in this moduli space, then this is of rank 1. And there are no other codimension 2 classes other than, so every surface is homologous to a complete intersection. These are all known. But the point here is that if you look at the middle part of the Hodge diagram, Hodge diamond for a cubic fourfold, then you will recover this part. So the middle cohomology for X. So we look something like this. And then, of course, you look at the non-trivial part, and you see that you have the same numbers as for a K-free surface. So this looks very much like the middle cohomology for a K-free surface. So H2 for a K-free surface, the numbers are the same. But nevertheless, the signatures are different, because here the signature is 319, whereas here the signature is 220. But having said that, there is a possibility, so you would like somehow to identify these, and there is a possibility of passing to codimension 1 sub-Hodge structure of signature 219 that would appear in both. For the K-free surface, it's clear how to do this. You have to pass to the primitive cohomology. But to achieve this for the cubic fourfold, you must allow another class that is not a complete intersection. So that's why in this attempt of kind of identifying Hodge theoretically cubic fourfolds with K-free surfaces, you must pass to neuter left special cubic fourfolds, which is a countable union of divisors in the moduli space. So let me just explain this. So for, maybe I should write there. Sorry? The primitive cohomology, yeah, that's right. Yeah, sorry. Of course. Thank you. Okay, so for an integer d, you look at CD. So these are those x in C, cubic fourfolds, with the property that there exists some surface such that you have an embedding, you can assume it's a primitive embedding of this lattice of rank 2 inside H22 xz. And d is the discriminant of this lattice. So if you want to relate cubic fourfolds to K-free surfaces, you must restrict to elements in these divisors. And it's a theorem of Hesset that CD is non-empty if and only if, so D, the discriminant, must be congruent to 0 or 2 modulo 6. And in this case, in which case CD is a divisor, is an irreducible divisor. So this Noether-Lefschetz locus is a countable union of CDs where D satisfy this congruence property. So C Noether-Lefschetz is the union of these. D bigger than 6. No, sorry, I think the first one is, yeah, I want something like this. This is a fake case, yeah. Yeah, 40, yeah. So C and L, 8 is the union of D such like this, of CD. Okay, and then, right, so this is these are the Noether-Lefschetz special cubic fourfolds. And then you can ask actually, so this is a necessary condition for this hope to be realized, namely of recognizing in the Hodge structure of a cubic fourfold a K-free surface. And now you can ask when you can associate a K-free surface to a cubic fourfold. And this has been achieved in a paper of Hesset, which is fairly well known. Actually, I'm sure people here who know it better than I do. So you say that X has an associated, so this X necessarily has to belong to such a CD, has an associated K-free surface. If there is such a polarized K-free surface S such that you have that the primitive cohomology of the surface as a Hodge structure is isomorphic to the orthogonal of H2 and R. And this is viewed inside H4 primitive of X. So this K-free surface is purely Hodge theoretical object, and it appears there via the Torelli theorem. You do not have, in fact, one of the problems in this correspondence is that, except very few cases, the K-free surface is not constructed geometrically. So this is the definition, and then it has it actually realized when this happens, and then there is a very strange-looking condition. So, so this is only a definition. So X has an associated K-free surface, has an S, if, well, so there is 4 doesn't divide D, 9 doesn't divide D, and no odd prime congruent to 2 mod 3 divides D. So this is a question, I mean, that certain integers are not represented by a quadratic form. So the sequence you have here, a sequence of integers. So this is 8, 14, 26, 38, 44, and so on. So these are the K-free-like cubic fourfolds. Okay. And then, well, so I don't have anything to say about rationality, but there seems to be a belief, which is an old belief. I heard it from Joe Harris something when I was a PhD student, that somehow this should be the rational cubic fourfolds, and there are conjectures of Hassett, of Kuznetsov, and so on. So there is a lot of interest in studying the K-free-like cubic fourfolds. But let's go back to the to my story. If you restrict further the degree, there is a further theorem of Hassett in the same paper, which says that, in fact, if the degree D, so D is this 2G minus 2, if the degree is 2 times, has this form, n squared plus n plus 1, then, in fact, Noether-Leschetz special cubic fourfold of this discriminant admits a polarized K-free surface SH in F. Well, had I chosen the other notation, I would have here D on the other side. So, but now I have to pass to D of this genus D over 2 plus 1, such that you have the following identification. You associate to X the Fano fourfold of lines. So this is the Fano fourfold of lines on X. So this is those lines in G15 that happen to line on X. So this has been introduced by Boville and Donaghy and shown to be a hyperkähler fourfold. So this fundamental object that you associate to a cubic fourfold, the Boville-Donaghy fourfold, is actually isomorphic to the Hilbert square of S2. And this is embedded in G15. So this is a summary of work of Hassett. So we are going to treat this. Yeah, I have still to say something. So the S here, this is an isomorphism of Hodge structure. This S is constructed Hodge theoretically, and except in very few cases, in fact, D equals 14, which is already treated in the original paper of Boville-Donaghy, S is not known what S is. We just know it exists one. It would be, of course, very interesting to construct S in terms of X. By the Hodge, exactly, that's right, by the Torelli theorem. But I know something. Actually, to finish this part of this recap on Hassett, I should say that there is a map between these two moduli spaces. Yeah. So for this degree, and this map is, in fact, 2 to 1. So the degree of this map is 2 if D is congruent to 0 mod 6 and of that type. And in fact, it's of degree 1. So birational isomorphism if D is congruent to 2 mod 6. So this is a very nice fact. because we have another handle now on understanding K-free surfaces using cubic fourfolds. And this is what we are going to use. So this is somehow, we regard this as some sort of gift that we got via, from Hassett, this theorem. And we are just kind of trying to draw some geometric consequences out of this isomorphism. Sorry? Exactly. Yeah, so the first case actually is 14, which is known. Yes, so there you have F8 is isomorphic to C14. Yeah? So this is the F8 that I already described. And in this case, the cubic fourfold is a Pfaffian, and the K-free surface can be reconstructed from that description. So this case is pretty well understood, and the cubic fourfolds of this discriminant are rational. So this is the old theorem of Morin. The next case is D equals 26. And there we have, via Hassett, we have this isomorphism. So F14 is isomorphic to C26. Yes, and the isomorphism, I just repeat. Yeah, so sends a K-free surface to X, where Fx is isomorphic to the Hilbert scheme of 2 points on S.
When you say isomorphism, you mean birational?
Birational. Everywhere, yeah. I mean, this is a statement about the birational geometry. So it's it doesn't make a difference. Yes, that's my next slide. So so the point is now that this Fx comes is embedded in the Grassmannian, therefore comes endowed with the Plücker polarization, and this Plücker polarization. So I have an O, but I view this Plücker polarization on the second symmetric product of the K-free surface, right? So maybe let's introduce some notation here. So on the symmetric product, I have the exceptional divisor. So I blow up the diagonal. This is delta. And this delta is a union over points P in S of rational curves, delta P. And this delta P is just a set of cycles in S2, which are supported entirely at the point P. Yeah, so this is a P1. I have a rational curve. So the rational curves, this delta P is fiber delta. And then the Plücker polarization, so I call it this gamma or OS2 of 1. So this is the Plücker polarization. It has been known that this is actually equal to 2 times F minus 7 delta. So delta is the class of the diagonal. And F is the so-called polarization class induced by the polarization of the K-free surface. So F is the class of those cycles that intersect a given curve in the polarization class.
Yeah, but I think it's half of the diagonal.
That's right, the diagonal, but it's the reduced one. The reduced diagonal, yes. So this is the class. Okay, so H is a fixed curve in the polarization. Okay. So this is what we know. Okay, so now I come with a very simple idea. Let's look at this delta P, right? You fix one of these rational curves. So you fix one point on this associated K-free surface, about which we really don't know anything. It's total mystery. We associate to it delta P. And then we see that by intersecting with the Plücker polarization, that this is a curve of degree 7 in the Grassmannian. Yeah. And now using the correspondence between rational curves in the Grassmannian and scrolls, delta P corresponds to a scroll R, which is, I call R index P, that is contained in X. So to any point on the associated K-free surface, you associate a septic scroll. So the degree of R is, of course, the degree of the associated rational curve. And as we established, this is equal to 7. So from points on the K-free surface, we associated, to each point of the K-free surface, you associate a scroll contained in the special cubic fourfold. And in fact, you can also go backwards, because it's a simple argument with the Boville-Bogomolov pairing that so it's a remark here, any rational curve R inside fx of degree, sorry, I don't think I use, let's call this gamma, inside fx of degree 7, right? So fx is embedded in the Grassmannian, and the degree is with respect to the Plücker embedding. Irreducible rational curve of degree 7 is of the type gamma equals RP. So there are no other septic rational curves in fx other than the ones coming from the fibration.
So you mean a smooth rational?
A smooth, yes. Okay. Yes, any smooth, irreducible, yeah, a P1. Yes, that's right. So these are considerations that, yes, I should have said this. Thank you. So this is an irreducible divisor, right? And these are considerations of a general element of that divisor. In particular, the lattice will be what I wrote there, rank 2. And that's a primitive embedding, a lattice of rank 26.
So there's a confusion in notation here. RP is what? It's the scroll.
Yes, thank you. There is a confusion. Delta. Yeah. So as a curve, yeah. So that, yeah. Okay, so to summarize this. For a general x in C26, I can identify S with the moduli space of 7 of rational curves of degree 7 in the fourfold of lines. Yeah. So this is some sort of identification. Of course, it's not ideal, because the Hilbert scheme of scrolls is not a very coherent.
What did you write?
M0. So these are rational curves of degree 7. Sorry. Rational curves of degree 7 in fx. Yeah? So I described essentially one direction, and the second one is just a lattice calculation. These are the only types of scrolls of degree 7.
Why do you say this is not finding the K3?
I mean, if it's a question, it's not at the level of it's a Hilbert scheme of scrolls in some cubic fourfold that you have Hodge theoretically. I mean, how do you write down a cubic fourfold of degree 27? Well, having the scrolls somehow. Well, in some sense, it gives the K3, yeah, but. Well, I said it is not a theorem in the style of Mukai. Mukai starts with a very concrete variety, like a Grassmannian, and takes a tautological vector bundle and says, well, okay, the sections of this, and you maybe cut it out, and then you get all the K-free surfaces. Well, this is a certain level of abstraction here. Okay. So now already this is something, so these were very simple considerations, and they were essentially there from the Hesse theorem. this already will give a short proof of the unirationality of M14. Because we just set up an incidence correspondence. I should say something. I can parameterize, of course, all these scrolls. I should have said something. I'm sorry, I forgot something to say. So if I have such a scroll in some x, I can look at the lattice. So the lattice looks like this. So I have h squared here, r, h squared, and r. So this is 3, this is 7, this is 7. So you want to have discriminant 26, so this must be 25. But then if r squared is 25, you can apply the double point formula. And assuming that the scroll has only ordinary singularities, from the double point formula, you will know that R will have 3 nodes. And these nodes are non-normal nodes. So they look like 2 P2s meeting in one, 2 C2s in C4 meeting in one point. So what you have to look, so these scrolls that have to lie on a cubic fourfold of discriminant 26 cannot be smooth. They are 3 nodal, so R is a 3 nodal septic scroll. So this is the main difference compared to the previous more classical case, F8 of discriminant 14, where you have quartic scrolls in the picture and those are smooth. So these are nodal scrolls. But okay, the number of nodes is small and we can parameterize the Hilbert scheme of such scrolls quite easily. So to have the moduli space of nodal scrolls, well, how do you get a nodal scroll? You take a smooth scroll of degree 7, so if it's of degree 7, then it will naturally lie in P8, and then you project from a 2-plane that intersects the secant variety of the scroll 3 times, and those points of intersection will correspond to the nodes. So this is not difficult to realize. So you start with a smooth R prime, I call this, a smooth scroll in P8. So this is smooth scroll. So this is of degree 7. So this is just in the classical notation, just S for free. Or if you want, this is just a blow up of P2 and a point. And then, yeah, so I'm sure everybody knows how to realize scrolls in projective space. You just look at the linear system. So the linear system that you have here is you look at the 4 times the line class minus 3 times the exceptional divisor corresponding to O. Yeah. So this I fix once and for all, the smooth scroll of in P8, septic scroll, and then I simply project. So how do I do this? Well, I choose points x1 on the scroll, x1, I, y1, x2, y2, x3, y3. So xi and yi are points on R prime. And then I choose further points. So these are points on the secant variety. And then I form this 2-plane. So here as A1, A2, A3. So AI are points in the secant variety of R prime. This plane is called lambda. And we project from this 2-plane, and we project to a complementary P5. And under this projection, so the smooth scroll lies in P8, and it gets projected to one of my scrolls, 3-nodal septic scroll in P5. So this is chosen generically. The points on the secant variety are chosen generically. And this is a 3-nodal scroll, right? Because, of course, you have that pi lambda of xi is pi lambda of yi, and this is equal to a node. So this is a, let's call this, I don't know, ui maybe. So this is a node on R. Okay, so you can, of course, set this up universally, this construction. It's a very simple and concrete construction. And then you get the moduli space of 3-nodal scrolls in P5. So I look at the So the Hilbert scheme of scroll, so let's call it this SCR, H scroll. So this is the moduli space of nodal scrolls in P5. So it's the septic free nodal. So by this construction, well, this will be birationally isomorphic to the symmetric product, the third symmetric product of the secant variety of the scroll, R prime. And of course, you have to divide out by the automorphism of R prime. But R prime is just the blown up of P2 at a point, so the automorphism group is 6-dimensional. Now, the secant variety of a scroll is a well-known object. It's a 5-dimensional variety. It has a determinantal presentation. I mean, we also studied it in our paper. This is a 15-dimensional variety. To summarize, this is a 9-dimensional unirational variety. So the parameter space of such scrolls modulo the automorphisms is a 9-dimensional unirational variety which has this rather concrete incarnation. And now I can go to the cubic fourfolds, and for that I have to set up an incidence correspondence. So this is the incidence correspondence between fourfolds and scrolls. So I have here, let's call this variety X. So I have on one side X and R, where R is a three-nodal scroll, so like that. And R is contained in X. And on one side, I have the forgetful map to the moduli space of scrolls. And on the other hand, you have the, so maybe this should be pi 2. And here I have pi 1, and this is the Hesse divisor.
So, excuse me, so you're saying that if I have a general septic scroll with 3 nodes, it is contained in some smooth cubic. That's what you're saying?
Right. In fact, more than that. It is contained in a P12 of such cubics. So this is a P12 bundle.
So I guess even if it only has 2 nodes, it is contained in
yeah.
It must be
But you look at the you look at the, these are the free nodal things.
Yes.
These are free nodal.
Yes.
Right? Okay. So now you look simply, so the fiber here of, you take 1. This is a projectivization of this vector bundle. This vector bundle you can compute, I mean, so this vector space. You can compute, this is a P12. So let's see, I think I don't want to go, well, it's an elementary calculation. You just look at, yes, you know everything how to compute this, right? You know, basically, you look at cubics, they have to pass through 3 nodes. You have 56 minus 353, and then you have to look at the condition imposed by the nodes. But you have everything here, this you pull back to P2, because the scroll that we started, we fixed once and for all, is embedded by this linear system. So this is an elementary calculation. So this is a P12 bundle. So now let's look at dimensions. This guy here is 9-dimensional. This is a P12 bundle over a 9-dimensional space, so this is a 21-dimensional variety, which is manifestly unirational, because the base was unirational. We are going to get, yeah, it will be, but yeah. So that's what we are going to prove it, but with a different argument. Okay, and then the fiber here, what is the fiber of X? Well, as I pointed out, the fibers here are the scrolls contained in X, and this is what I described on that blackboard over there. This is the space of rational curves of degree 7 in Fx. So this is what I denoted M0 Fx7. And this is S, so to say. So to summarize, this X that I constructed here is the universal K-free surface of genus 14. Yeah, birational. And the statement is that X is unirational, right? Therefore, this is also unirational, but we can do more. I also have 15 minutes, yeah, so I'm not yet finished. But this argument, as I say, establishes the unirationality of the moduli of the universal K-free surface. Now we are actually going to show that this is rational, but with a different argument, and for that we go back to Mukai and genus 8. Well, I mean, had I known to do it, I would have done it.
Well, maybe you're just hiding it from us. I don't know.
No, I don't think. I am not hiding it. Not that I know that I'm hiding it. Yes. Yeah. Well, I mean, it was not for lack of trying that we. But I can prove that something is rational, namely this one. So, so the rationality of H of this. And actually, this we were surprised how quickly this works. I mean, how easily this works. Okay, so I have to start with a scroll. Again, so this is one element here. So this is a three-nodal scroll. And I go back now. So to this, I associate this curve gamma. So this is the curve that is the septic curve in G15. So this is a septic rational curve. The curve of rulings. So gamma is the curve of rulings, right? So you put all the lines together, and then you get a curve in the Grassmannian. This is a rational septic curve. So this will span a P7. And this P7 will be embedded in the P14, in the Plücker P14. Now I have to express the condition that the scroll is free nodal. So what does it mean that the scroll is nodal at a point? Well, it means that if the scroll is smooth, then all the rulings are pairwise disjoint. If they have a node, then two rulings are incident. And this will happen 3 times. So if at one of these nodes that I considered here, I have actually 2 rulings of the scroll, Li prime and Li double prime, 2 rulings that are incident. And this is a singular point of the scroll. But then I can consider the 2 plane spanned by these 2 lines. Right? So let's call this pi I2. So this is the plane spanned by these 2 lines. And then you see that if you take all the lines in this P2 that pass through this point, that is going to be a line of lines, a rational curve in the Grassmannian, which is actually a line in the Plücker embedding. So I take all the lines passing through this point. I make them, color them with red. Yeah? And this will be, now this is Li, capital Li. This is the set of all the lines passing through Ui and which are contained in this 2 plane. So this is a line. So this is inside G2, G15. So this is a line in the Grassmannian. Yeah? So this is a basic factor of the Plücker embedding. You take the lines, passing lines in P2, in a P2 passing through a given point. This is a P1, which is actually embedded as a line in the Plücker embedding. So, and vice versa. This is, what is the property of this line? This line, Li in the Grassmannian, intersects the curve of rulings in 2 points. The points are there, Li prime and Li double prime, the 2 rulings of R that correspond to the node. So what is the condition that the curve of rulings corresponds to a nodal scroll? It is that there exists a line in the Grassmannian, a line in the P14 that happens to lie in the Grassmannian, which is furthermore bisecant to the curve of rulings. So this is the main geometric input that we use here. So I write it here now. So we have the following picture. So this is the most important picture of the talk. So we have the this curve of this rational septic curve of the rulings of the initial scrolls. I have 3 lines in the Grassmannian which are bisecant to this curve of rulings. So the points of intersection are Li1 prime, L1 double prime, L2 prime, L2 double prime, L3 prime, L3 double prime. Obviously, because the lines are bisecant to gamma, they will lie in the P7 span by gamma. So Li is in this gamma. But then what have we learned from Mukai in genus 8? We have learned that if you have G26 or G15 lines in P5, the Grassmannian of lines in P5, and you intersect it with a P7, you get a curve of genus 8. And that's what we are going to get here as well. So far, we only see bits of this curve of genus 8. But if we do the intersection of this gamma with G15, certainly we'll get gamma, we'll get L1, L2, L3, plus something else. And this residual curve I call B. The Grassmannian of lines in P5 has degree 14. This is of degree 7. This is of degree 1, 1, 1. Therefore, this is of degree 4. And I just have to make it pictorially. So this will look like this, actually. This is B. OK. So now you have to think a little bit, how does it intersect these other components? And it does it exactly like in my picture, which means that there will be further rulings of this, further lines through those, in those 2 planes that are, so this will correspond to some scroll, to some quartic scroll. And it is unisecond to these lines. And then it has to intersect the rest in 3 other points. So yeah, so the claim is now that, so as I said, so B is a smooth rational curve. The degree of B is 4. And essentially, very important, B intersects each of the Li's in 1 point. All these things to prove are very easy if you assume that this configuration can be realized on a K-free surface. Then it becomes an exercise in the Picard lattice of that K-free surface. And of course, you have such a K-free surface by the surjectivity of the period mapping. So it's a K-free surface with Picard number 5, where the polarization has this thing. And then you have to do some work to show that, in fact, that K-free surface, of course, this is highly non-general, but that this K-free surface is nevertheless a section of the Grassmannian. But so Mukai gives a sufficient criterion for a K-free surface to be a section of the Grassmannian, to be what's called Brillouin-Noether's general. And that's an exercise in the lattice, that certain vectors are not represented in the lattice of this K-free surface, which we do. So all in all, to the picture, to gamma and the 3 nodes, the 3 nodes correspond to these lines in the Plücker embedding. We have associated a rational quartic curve, which corresponds to a rational, to a quartic scroll. And now we just go backwards and we'll get our rationality result. Maybe I... So now I start with B. So start with a scroll with a smooth quartic scroll RB in P5. So this is actually just S22. So it's P1 cross P1 embedded by the linear system 2L plus M. By the automorphisms, I can rigidify this. This is fixed once and for all, right? The curve of rulings of this scroll is B, is the curve of rulings of this scroll. And now you just read this picture backwards, starting from these points. L1, L2, L3. Basically, that means that in each of these planes, there will be one of these lines will be passing through the node of R. R is not yet constructed, only B is constructed. You now single out 3 rulings of the scroll, of the scroll RB, L1, L2, L3. So single out and fix 3 points, U1, U2, U3 in B, in RB, sorry. The RB is the scroll, it's in P5. Then to this will correspond rulings, L1, L2, L3. These are rulings of B. Yeah? Okay, then you have to form the lines capital L, I. For that you have to choose now, so here is UI, here is Li. You have to choose a 2-plane in P5 passing through this line. So now choose, so you have a 2-plane. So this is what was I called, so let's call this P2I, contained in P5, passing through these lines. And then if I had this to each, so this is this gamma I, then I can construct, I can look at the lines passing through my point UI, and then I will get the lines capital Li. So what is the choice for choosing these 2 planes? You have a line in P5. You want to look at the P2 that passes through that given line. That's a 3-dimensional projective space. Yeah? So P3I is the parameter space for the P2 that contains one of these lines. Yeah? So maybe I should repeat. I start with my quartic scroll. I fix on the quartic scroll. The quartic scroll is fixed once and for all. I fix 3 points. Those I can also fix once and for all. Then these will end up being the nodes of the residual scroll R of degree 7. Then to the points correspond 3 rulings. Those are also fixed once and for all. So far I have not done anything. I mean, I have not moved anything. Now I move, I have to make the moduli of these lines in the Grassmannians, capital L1, capital L2, capital L3. I choose P2s containing this Li in P5. Each of them can be chosen, there is a P3 worth of choices. But then I am done, because I have B, I have L1, L2, L3, and from the yellow equation, I can define gamma as the residual, where I intersect B, this semi-stable curve with the Grassmannian, and gamma is the residual. So now I just have to summarize. So the theorem here is that, so with Sandro, is that the parameter space of such scrolls is isomorphic to the product of these 3 projective spaces, P1 free cross P2 free cross, P3 2, yeah? P3 3. And of course, I have to mod out by the action of the symmetric group. And the symmetric product of projective spaces are known to be rational. This is rational. Yeah, so it's 9-fold, 9-fold. Okay, and then you conclude that from this that, in fact, F14, which was, there is this Zariski trivial bundle over this H scroll, this is also rational. Right. So the proof, this is the idea. There are things to check, of course. One thing to check is that this, so which I have not explained, is why this B, this quartic scroll, is in fact the generic situation. It could also be the scroll F2, corresponding to a Hirzebruch surface F2. It's actually not, it's F0. Basically, we have to show that if you take the K-free surface with this property generically, all the lines on these scrolls correspond to the rulings. That distinguishes the rational quartic scroll F0 from F2. So this we do. And then we have to show, of course, that the Mukai construction works in this at this level of degeneration, but this is a lattice calculation which we carry out. Thank you.